I would like to introduce the idea of the directional derivative, but I thought we'd start just by talking about derivatives and partial derivatives, these instantaneous rates of change, these slopes of tangent lines that we've talked about already. So in Calc 1, we meet this idea of starting with a function graph and taking the limit as delta x approaches 0, the distance here in the domain approaches, the distance between these 2 points in the domain approaches 0 of the slope of this secant line. When that limit exists, we call it a derivative, and it's an instantaneous rate of change, and it's the slope of a tangent line. In this course, we turn this into partials by saying, well, for the partial with respect to x, let's treat y like a constant. So that's kind of what I'm picturing over here. I've assigned a line parallel to the x-axis as the value y equals y naught. So I'm treating y like a constant, and then I just do the same idea of derivative, but only in the x direction. And what I can imagine is that this is like having this picture, but turned around so that this is the horizontal axis and z is the vertical axis. Right? When I trap y equals y naught there, I just get a 2D picture in the plane y equals y naught, and that's still the idea of derivative I have. Right? The total amount of distance in the domain, and then I'm finding the difference in the corresponding z values. Right? So I have x marked here and x plus delta x, an increment, and then the corresponding values that I could imagine a secant line running through. Limit as delta x runs to 0, and I get the slope of a tangent line in that plane. For the partial with respect to y, I think about x being a constant, and I have that same idea, right? Where now I have a plane that would intersect my curve like that, my surface like that, giving me a curve that I can then think about kind of just taking this picture and turning it like that and having the same idea of slope. So every definition here, right, I have an amount of change in the domain, right? That's what I'm dividing by, and then the corresponding points in the range, the points that correspond to changing just by delta y or just by delta x. So what I want to talk about now is what we call a directional derivative. And to start, we'll work with a function on two variables. So the main idea is that the domain here is some set of points in the plane. I want to imagine a point x naught, y naught. And I want to calculate the derivative of f, but not with respect to the x-axis or y-axis. I don't want one of those partials. I want to imagine that I'm finding a rate of change as I travel down an s-axis, right? Some other line. And so the idea here is I need to figure out what it means to increment on this line by an amount delta s, so that I can define a derivative in terms of that quantity, that delta s. So we could actually imagine parameterizing that line. So if we think about what we need to parameterize the line, I would need a vector parallel to the line and a point on the line. Well, I've already identified the point, so let's just say we know the vector v is parallel to our line. Then we could parameterize our line. This would be the line x equals x naught plus v1 t, and y equals y naught plus v2 t. All right, so let's imagine we want to increment on the s-axis. So let's just imagine having plugged some value of t in there, and we'd get a different point. And that would simply be the point x naught plus v1 t for whatever value of t we plugged in. Every point would be in this format. I'm interested in the distance we've traveled, right? Because I want to be able to call it delta s. So now what I realize is to find the distance between these 2 points, I'm subtracting their x-coordinates and y-coordinates and following the distance formula. So the distance between those 2 points would simply be v1 squared t squared plus v2 squared t squared. I can factor out a t. That would leave me with v1 squared plus v2 squared, which is the magnitude of the vector v. Right, whatever value of t I plug in there, I've moved by this amount. So what I'm thinking is I want to be able to call that delta s. And I don't want it to depend on the length of the vector v. So I want to get rid of this. And the easiest way to do that is by saying, hey, instead of using vector v, let's use a unit vector that has the same direction. So I'm going to define the vector u to be v over its own magnitude, that unit vector with the same direction. And for convenience, I'm going to call its components u1 and u2. Right, where I know u1 is v1 divided by the magnitude of v, and u2 is v2 divided by the magnitude of v, just to make our statements a little easier. So now I'm thinking about this u as being a unit vector that has the right direction. Let's reparameterize our line. Instead of v1 and v2, I'd use u1 and u2. My distance calculation now has those u's in it. And instead of having a magnitude of v, I have a magnitude of u, which is 1. And so now I know the distance I travel for every value I plug in for t is just t. That's the amount. So if I want to change by the value delta s, I just need to let t equal delta s. So my definition for directional derivative will involve that idea. So, the derivative of f with respect to s, thinking about that s-axis, and I need to be descriptive. In the direction of a unit vector u from a point p naught. U is a unit vector. And p naught is that point. So this, literally, the derivative of f in the direction of the vector u from the point p naught would be equal to this. The limit as delta s approaches 0 of a whole bunch of stuff over delta s. And now what I need to think about is what to plug in. Well, if I move delta s down the s-axis, I ended up at a point right here that happens just by plugging delta s into these parametric equations. So x naught plus u1 delta s and y naught plus u2 delta s. Minus, well, the z value at x naught, y naught. And there's my definition of directional derivative. The derivative of f of x comma y in the direction of the unit vector u from the point p naught. That is my definition of directional derivative. In our next video, we're going to do an example or two where we actually take a derivative using this definition.